Hello, my name is Mitchell Katz, and I am with the Water Sciences section of the Natural Resources Management part of the Orange County Environmental Protection Division. I've got a brief presentation today to discuss some of the work we've done in the northwest of the county. And the work was done in an effort to identify sources and seasonality in nitrate concentrations in our groundwater resources and in our freshwater resources at Wakawa Spring, and then to provide some data-driven recommendations. So let's enter the presentation. To give you a little bit of a background, way back in 2008, the Wekiva River TMDL was written by the Florida Department of Environmental Protection. And a TMDL is a total maximum daily load. And this load it describes a threshold where below the threshold, you can add a pollutant, like a nutrient pollutant, and the river system or the freshwater body or the canal or the water body in general should be able to assimilate that concentration without any kind of noticeable side effects or deleterious side effects. Above that TMDL, then you start getting some side effects that maybe you really don't want to see in your freshwater bodies. During this time, during the derivation of this 2008 TMDL, the Florida Department of Environmental Protection identified septic tanks and nitrogen fertilizer application as the two largest sources of nitrogen nutrient pollution to the water resources of this region. Subsequent to that, Lake Jessup, that was incorporated into a BMAP, which is a Basin Management Action Plan. Lake Okeechobee, that BMAP was adopted. And the significance of these basin management action plans is that they are, once they're adopted by the state, the counties or the stakeholders, jurisdictional stakeholders, cities, townships, the county, are responsible for reducing the amount of nutrient pollutant described by the BMAP. In 2016, the Florida Springs and Aquifer Protection Act was passed, and that required, as you see here, an adoption of a model fertilizer ordinance language that was posited by the Florida Department of Environmental Protection. And we had to do that by July 1st, 2017. So we went to the board at that time, and that model ordinance language was adopted. At the same time, BCC asked EPD to look further into sources of nitrate loading within this area. And finally, here, the last bullet, you can see in 2018, the Wekiwa and Rock Springs BMAP was adopted. And within that BMAP is this Wekiva TMDL, which is a threshold of like 0.286 milligrams of nitrate and nitrogen per liter. And that's the threshold that we're supposed to achieve. Okay, just to look back a little bit here, this is the results of DEP's assessment of the nitrate sources out there. Excuse me. And you can see here that, looking at the legend, you can see here that about 26% of the loading of nitrate nutrient in that basin is due to urban fertilizer application. And this is primarily fertilizer application to urban turf grasses. So you end up having nutrients, phosphorus nutrients, nitrogen nutrients that are entering these waters. And what happens? Well, what happens is that EPD collects water samples from their water bodies, reports to DEP. DEP in Tallahassee looks at those results And they say, well, is there a problem there with the water quality? Is there some sustained elevated concentrations of these nutrient impairments? And they come back to us with a list of water bodies that they believe to be impaired. Currently, we have about 154 total impairments. Some water bodies have multiple impairments. And there we go, 17 nutrient TMDLs. And those are TMDLs that the county is obligated to, reduce the loading of these pollutants into the water bodies. And of course, 5 nutrient B maps. And many of these nutrient B maps are the result of the hydrogeology that Central Florida, where it's located, where Orlando and Orange County are located. If you look at Florida, you'll see that much of Florida is an old, marine reef, and Orange County sits on top of that reef, and that old reef, and the groundwater flow direction is out from Orange County. So, all these water bodies flow from Orange County. The important part to look at here with respect to impairments is that these cumulative impairments established by FDEP, you can see through the years from 2002 to 2020 that overall there's an increasing trend. As land use changes, as more people move into the area, you start getting more and more impairments to these freshwater bodies. Currently, the cost per pound for removal of these nutrient improvements is highly variable. It depends what the nutrient pollutant is. It depends where it's at, but they range in general between $165 to $10,000 a pound of nutrient removal. And this range is exclusive of the costs it takes to assess a watershed or to see which best management practices would be effective in removing it or creating an engineering design. This is just kind of like once you got that engineering design in there to remove the pollutants, that's kind of like the range of costs there. And as everyone knows, costs only increase. So what you're looking at here now is a site vicinity map of our study of the area. And remember I said back in 2008, DEP had done some work out here to see what some of the sources of nitrate loading were. Well, to that end, DEP and the St. Johns River Water Management District created this series of shallow wells, here illustrated in green, that they could grab groundwater samples from and then send them off to the lab and have them tested for a series of parameters, including nitrate. In 2017, Orange County, at the request of the BCC, expanded this investigation by adding intermediate depth wells of intermediate depth, shown here in yellow, and then also a couple of deep wells, shown here in blue. Also, I want to mention that DEP had come back out here and installed some deeper wells like this XDEPF LD up just west of the park area. So why did we do that? Well, we wanted to see how the nitrate, or if it's there, where it's at, and how it's moving. In order to assess where things are, you kind of gotta get your arms around it and find your clean edges, or at least determine, how far horizontally the problem might be and how far vertically the problem might extend. And if you look at this cross section is typical for the area we looked at. The aquifer, or the groundwater system, I should say, is comprised of three distinct layers. The first is the superficial aquifer system, and that's the aquifer that's closest to the surface. And you can see over here, like MW17, that's a shallow well that was installed. There's a screen right there where the water enters. Where that's installed in the shallow aquifer. Whereas some of these wells, like here, XDEP PBS, is installed in the next layer down, which is the intermediate aquifer system. And if you look even deeper, like this XDEP PBD, that is even deeper in the upper Florida aquifer. The upper Florida aquifer is the aquifer that provides Florida. It's a very productive aquifer. It provides Florida with a lot of fresh water. So again, this is a cross section, and this typical cross section varies in thicknesses and depths throughout the county. So we went to our wells and we collected groundwater samples and we sent them off to the laboratory for analysis, and we got the results back. And we did this for like quarterly events, triennial events between 2017 and 2021. There was a survey that was done by the University of Central Florida back in 2009, and they surveyed residents about their fertilizer use. Some residents had no idea as to the fertilizer that was being laid down on their property. Others didn't fertilize at all. And in between, we had answers in terms of they knew the use, they didn't know the use. But in general, it looks like people were applying fertilizer like in March, April-ish, and in June and July, and also maybe like October, September, kind of in those windows. So we did our sampling during those times. Sometimes we went quarterly to get a little bit more information, more data. But what you're looking at here are the wells grouped by their depth. In other words, we just saw that the aquifer can be broken up into shallow, intermediate, and deep wells or deep groundwater. And here are the results of the water quality in those three zones. You can see that the concentration of nitrate in the superficial groundwater, superficial aquifer system, it varies depending on where that well is located. Same thing can be said in the intermediate groundwater aquifer, and same thing in the deep water. We had about 25 locations that we tested. Of those 25 locations that we tested, 17 of those locations, or about 68% of the locations we tested, were above this red line. This red line represents the TMDL for Wekiwa Springs and Rock Springs. So what we see here is that the concentrations that we're seeing in the groundwater are a lot higher than that TMDL. And Orange County is obliged to achieve that TMDL, and that means lowering the concentrations that we see in groundwater. And I just want to remind you, this, if you look here at this label on this axis, this is the average nitrate concentration. So what you do not see here in this graph are the maximum concentrations of nitrate found in these wells. You're seeing kind of like on average how the wells behave, or the nitrate levels in those wells on average. So speaking of behavior, we also looked at this MW7. We got a lot of results from this MW7. It was always producing water. It always seemed to have nitrate in it. So we kind of looked at that well, maybe as a surrogate for the other wells. So in this plot here, if you look at this, you've got a time on the x-axis, and this is the month of the year. And on this y-axis, you've got rainfall inches ranging from 0 to 14 inches. This blue line represents the county-wide average rainfall in inches that is reported by the St. Johns River Water Management District. This secondary axis over here is the nitrate concentration we found in well MW7. So this orange line, again, represents the nitrate levels in MW7. And what do you notice here? You notice that when the average precipitation increases, there's a little bit of a lag time, but it appears that the nitrate levels in well MW7 increase as well. As those rainfall amounts start to fall, what do you see? You see that the concentration of nitrate in that well, MW7, tends to fall as well. And so you get this kind of mirroring it doesn't map strictly, because look at this. Here you've got high nitrate concentrations and you've got low rainfall. This could be explained by maybe, since it was low rainfall, the residents are irrigating a little bit more. So there's some factors that go in here that affect the variability of what you see, but it looks like the two curves correspond. That's to say that when we see higher rainfall, we see higher nitrate concentrations in the ground. So moving on here, if we zoom out and we look at all our wells that are in the shallow zone, we see something similar. This box, this green shaded rectangle, represents the proposed fertilizer restriction period from the end of May to the end of September. This red line represents the TMDL again. This dashed red line is always going to represent that threshold we have to hit. But what you can see here in the takeaway is a couple things. In the shallow zone, you're seeing that there's big differences in concentration from well to well. And that's because the wells are located in different areas. There's different land uses. There's different geology. There may be different biological mechanisms going on in the soil. But in general, you can see, if you follow these lines of concentration, that when you hit the summer months, the rainy, wet season in Florida, what do you get? You start seeing these peaks in concentration again, in nitrate concentration. Even in some of these wells that have lower concentrations, like MW1 here is the well with the little star on it. If you follow this, you see a lot of the times it looks like it's low, but then it pops up here at the end and it's above that threshold. So this is all nitrate mass going into the groundwater, headed to the spring, or headed to the water body, basically. And of course, you can see these other concentrations peaking in the summer as well for some of these other wells. Now, we go deeper down into the aquifer, and we're in the intermediate zone, and we get the spaghetti. Well, what this is showing here, that it looks like this because, again, there's a lot of variability in the concentration data we have, because it depends on well location, it depends on what's happening at the surface, it depends on the geochemistry, all that kind of stuff goes into it. But what do you see? You see that against the wet season, this green rectangle, that we're seeing peaks in nitrate concentration. We'll go deeper down and we see that we have the upper Florida aquifer. A lot of these wells in the upper Florida aquifer have very small amounts of nitrate, and that's because, they have very low concentrations of nitrate. That's because there's a lot of water in the upper Florida aquifer. So the nitrate mass is there. However, it is diluted by the huge amounts of groundwater that the upper Floridan is pushing towards the spring. Remember, it's the upper Floridan that pushes this water and it pops out at the spring. So what do we see here again? Here's our red line, the TMDL. And what do we see again? This well here is the DEP well, the DEP installed, and we have a nitrogen peak in September. Here we have MWBU. This is a well that the county installed. And what do we have? Well, we've got peaks here in April, but the major peak, which coincides with the UCF study where they were fertilizing, right, reporting fertilizer usage. And here is another peak in, say, July, which also agrees with that period in the UCF study. And it's like the maximum. And then, of course, we're tailing off to the end here, and it's up again here in December. So again, we're seeing increases in nitrogen concentration during the wet summer months. Okay, well, so what? Well, the next thing to do is to kind of look and see where it comes from. And I'm going to back up a second. I'm going to talk about isotopes. What isotopes are? Isotopes are different weights of the same element. And this is the most simple isotope known to us so far. This is hydrogen, and hydrogen is very abundant. And this is the basic hydrogen number. It's isotope 1. If we take a neutron and put it on this proton, then we kind of like double the weight of the hydrogen. And this is a hydrogen 2. And if we add another another neutron, then we have a hydrogen 3. And these 3 species, hydrogen 1, hydrogen 2, and hydrogen 3, are 3 isotopes of the same element, hydrogen, but they have a different weight. And because they have a different weight, they can be separated chemically. And that's what we did. We took those wells that had sufficient nitrate in it, collected those samples, and sent it off to a lab that could tell us how much of the isotope of nitrogen 15 and oxygen 18 were located, how much was present in the sample we sent. Why did we do that? Because when we plot this up, basically make the ratio of nitrogen 15 to oxygen 18, we get kind of a unique signature. And that signature can tell us about where the nitrate came from. And so what did our signatures tell us? In MW7, here's our friend MW7 again. This is the shallow well. A lot of these dots land in this box that's labeled ammonium urea fertilizer. You don't see too many up here with the synthetic fertilizer, and you don't see anything over here where manure and wastewater would show up. They fall here in this box. We see the same thing happening with MW22, which is it's in the intermediate zone located in a residential area. We see the same thing happening with MW11 here, which is in a residential area. We see the same thing happening with MW4/4R. This is a replacement well because this well jammed up on us. We have many hits within this box. Now, remember I said what you see depends on the geochemistry. And part of that geochemistry has to do with bacteria that are in the groundwater. Sometimes during the year, there's different bacteria. There's different amounts of oxygen and different amounts in the groundwater, and different amounts of bacteria kick in and kick out. Those bacteria work to change the ratio or the signature that we see in the results turned back to us from the laboratory. And that's why you see that not all these green circles from MW7 fall in here. It could be that we were out there at a time of year when a process called denitrification, which basically reduces the amount of nitrate or changes this nitrate signature, is prevalent. But the signature tells us, the signature following this line, this diagonal line across the top indicated by these two lines, tells us that originally it came back from this box. In other deeper wells like MWBU, or let me see, where's it? This is a good one here, SW1, Wekiva Spring itself. The water is a mixture of nitrate from different sources. And that kind of is shown up here in the scatter of the points. Like this point's way up here, right? We have a different mixture up here. What this tells us, basically gives us this isotopic signature gives us a fingerprint as to where that nitrate comes from. All right, so we know that we see nitrate in groundwater in our wells. We know that we see groundwater, the concentrations, peak in the summer wet season. We know that we can identify some sources. Some sources are directly related to the nitrate fertilizer put on that lawn. Other sources are more mixed in the deeper wells. So how much does every source indicate or contribute, right? And to answer that question, our contractors created a mixing model which was based upon the mixing model. Basically answers the question, okay, we have nitrate in this well. How much comes from fertilizer? How much comes from septic tanks? How much comes from reclaimed water? Where's it coming from? So we start with this model, and here's our nitrate anion. The red is oxygen, the blue is the nitrogen. We came down this pathway here. We talked about the isotopic signatures, and our signatures suggest that what we're seeing out there is coming from fertilizer that's applied to residences or to turf grass. This mixing model is based on Bayesian modeling, which, to cook it down, is like, okay, well, I've seen nitrate here before in this well, and I'm going to assume that a certain amount was from this source, and a certain amount was from this source, the other sources, and what does that say about going forward in the future? So you put in your concentration data, and out comes your proportions of nitrate due to each of the sources. And of course, there's more than two sources out there. I just, for the sake of brevity here, to get everything on one slide where it's legible, I just have source A and source B. So let's see what the Bayesian model did for us. So here's the Bayesian model. And this is known as a box and whisker. And just to step through this really quickly, what this is telling you, or what this is illustrating, is here's our box. And this line right here is like the median concentration we see. Here we see maximum concentrations. Here we see minimum concentrations. These little dots here are the outlier. So our outlying concentrations. So what do we see here? Remember MW4 from over here? Well, let me back up even further. Remember the average for MW4? I'm sorry, right here was 10. Well, we saw that, the concentration can be quite a bit higher than 10. And now we're seeing in that particular well that about 68% on average of that nitrate in that well is due to urea fertilizer or nitrogen fertilizer being put on turf grass. And you can look and see that these remaining shallow wells here, where we looked, here's MW7, we're getting above 50% as well. So now we're seeing that that groundwater, that nitrate we saw in that groundwater, a high proportion of it is due to the application of nitrogen fertilizer to turf grass areas. All right, so then of course we couldn't stop there. And what we did was we tested the current ordinance to see if it was protected. And the way we tested it was we had that data from MW7. We have the current ordinance. The current ordinance allows users to put down a 1/2 pound of freely soluble 0% slow release fertilizer per 1,000 square feet, or 50 or a pound of 50% slow release fertilizer, or a pound of 65% slow release fertilizer per 1,000 square feet. And just to back up a second, a slow release nitrogen fertilizer is a fertilizer granule that's coated with a polymer or a plastic or some other coating, a formulation, usually proprietary, that will slowly dissolve when in contact with water. And as it dissolves, the nitrate in that granule, that coated granule, goes into pore water and is available for the roots of the turf to uptake for growth. So again, our current code says that you can use a 1/2 pound of 0% slow release, or freely soluble fertilizer, or 1 pound of 50% slow release, or 1 pound of 65% slow release per 1,000 square feet. So that's the loading we used. We use this hydrous model, which was developed by the United States Department of Agriculture. And this model is used by farmers and other people in the agricultural community to kind of determine when they need to fertilize, how much water, that type of thing, so they can kind of fine tune the resources they deliver to their ag fields. We took a 2-year rainfall record recorded at Orlando International Airport, and we selected a particular 2 years that were neither drought years or excessively wet years. We went like an average kind of rainfall scenario. And then we simulate the nitrate leaching from 3 pounds per 1,000 square feet. And the reason why we used 3 was, going back to that UCF study, if you're allowed to put in, say, the 1 pound of the slow release, and you do it 3 times a year, you're putting in 3 pounds that year, or 6 pounds during this 2-year simulation. And so here's what the model predicts. If you're using freely soluble nitrate fertilizers, about 45% of that fertilizer applied is going to be uptaken by the roots of the turf. And that's roughly about, what is that? That's probably about 2.7 pounds of what you apply per 1,000 square feet. The roots will use, will bioaccumulate. But over 50% of that load will be available for leaching. And another 5% will be available for, it's just tied up in the soil, like in the organic cubic matrix. Well, the picture improves a little bit once we start using the slow release fertilizers. The current ordinance says that you can use 50% slow release, and let's see what the uptake is there, just under 52%. So we've gone from 45 to 52% of the nitrate fertilizer applied is uptaken by the roots, but still 40%, a little bit over 40% of that fertilizer put down is available for leaching. And this leaching primarily occurs with rainfall, right? It's the rainfall or excessive irrigation that is washing these fertilizer salts out of the soil and into the groundwater. And finally, if you use the 65%, we improve a slow release nitrogen fertilizer. You see that it improves a little bit more. We go from 52% up to 53%, but still we've got a lot of leaching going in. So this particular picture emerging from our hydrous model developed by USDA would suggest that the current ordinance is not as protective as perhaps we may want to have it in order to protect water bodies from excessive nutrient pollutants. So just to summarize here real quick, in 2017, the Orange County BCC tasked EPD to look at these sources a little bit closer. What are the sources of nitrate out there? And to that end, we engaged contractors to work for EPD to go ahead and collect groundwater samples and do some data analysis, do some data modeling, and tell us what they came back with. We actually had one contractor do like a peer review of the work that a third-party peer review work of what the prime contractor was doing, and the description of their work and the analysis and the summaries were contained in these three primary reports. The Wakata Spring Check Groundwater Monitoring and Data Analysis Summary, that was done by Wood. They were the prime on it. And this is Drummond Carpenter that did this peer review here, this gap analysis and peer review. And then Drummond Carpenter also did some groundwater modeling for us. And I didn't get into it, but it shows that the groundwater modeling they did was, if you take those concentrations you see in MW7, they go down vertically And based upon this groundwater model that is commonly used by stakeholders throughout Central Florida, the nitrate pops up at the spring, and it contributes to some of the downstream effects of excess nitrogen pollution there. So what were the study findings? Well, the groundwater nitrate concentration we saw back in 2017, 2018, 2008, which were above the 0.286 milligrams per liter TMDL, they're still out there. They're still high. And that suggests that there's an ongoing source of nitrate that's moving into the groundwater and with the groundwater and emerging at the spring. The isotopic work that was done out here, it indicates that nitrogen fertilizer is a major source of nitrate detected in these groundwater monitoring, and where we collected those samples. And that's consistent with what DEP said. We saw that in our time series work, those plots, we saw that the nitrate rate concentrations or levels in those monitoring wells we looked at, they show peaks during the wet season, which is primarily, like end of May to the end of September. And our contractors there's many recommendations in the reports, but one of the recommendations they came out with was that additional restrictions to the application of fertilizer to turf grasses during the wet season are warranted. And that restricted period may help us with reducing nitrogen leaching to groundwater and ending up in our water bodies throughout Orange County. We saw that we have over 140 water bodies that are impaired by nutrients. And it's kind of like a pollution 101 is that you address the source of it, because economically cleaning up pollution at the source is less expensive than cleaning up pollution at the final terminus where it's reaching. Okay, so what are our next steps? EPD is going through a process right now of collecting comments from our stakeholders and synthesizing responses, and we're going to publish those. We have an upcoming meeting with the BCC at the stakeholders meeting on November 30th, and EPD will get additional guidance from the BCC as to which way we want to go with this. We'll report our results out, and we'll get instruction from BCC.